Okay, please feel free to start, Professor Marcos.
Yeah, now I will present you another research combining very high cycle fatigue with temperature increasing during the tests. It was also a question, a task that during today in the morning also in the previous presentation, there was this discussion, how is the temperature in that? Because you know that during, okay? No, iPhone foi ou não? That you know that during the high frequency in the material, you have a strain rate very high, and it becomes in temperature increasing with the material. For this sense, it's always important to keep control of the temperature during the test, to don't modify the parameters or the material's properties. So dealing with this problem, exactly what's the problem of temperature during the testing, say some experimental results concerning the distribution of temperature during the curves, during the number of cycles. A equation using the first law of thermodynamics to try to find the heat dissipation during the testing, and artificial intelligent modeling to try to find how will be the temperature increasing, and also to performance, as we can see, that there is a combination of various parameters during the test. So one of each parameter contributes with something to the increasing of the temperature. So here we can come direct from here. We have a temperature versus number of cycles to failure. We have the phase one. Here we have a gradient of heating of the specimens. Then it goes, the gradient is lower here, and then it increases again until the fracture or the stop of the test. This high frequency, it causes specimens warm up. So it should be controlled by a cooling of the specimens, sometimes with water, with air. But sometimes it's possible, or it be not good for that, but it happens, a burn, a overheat of the specimens. It means that the properties of the materials are very changed during the testing. So what is going on with that? No? And if you have this difference in the properties of the material, you have also influence on the fatigue performance of them. So what I try to show you is exactly this modeling of the experimental that you fit up, and together with a modeling of artificial intelligence to combine the specimens properties and also the tested parameter. So the material was structural steel, with this chemical composition on these mechanical properties here. Here is the specimen also, in the same geometry. It's not the geometry is okay, but if you have a change in the elastic modulus of the material, you change also the dimensions of the specimens. Is another discussion after to come back for the discussion, because if you have during the manufacture additive, you have so change in the elastic properties of the material, this is very difficult after that to achieve. So you can lose every specimens that you have. And here we have the test conditions. 16 specimens are -1, 20 kilohertz of frequency. The goal was 10 to 7 cycles. So use 4 stress amplitudes according to the material's properties, according to the material's ultimate strengths, and also for different conditions of pulse and pulse. It means that during the testing, it's impossible to have the pulse all the time because the temperature of the specimens go so high, up so high. So we try to load the specimens during, for instance, 300 milliseconds and a pulse of 200 milliseconds, and you can change here as you want. That's the situation. So for sure, if you use pulser longer as the pulse, you will exchange your time for the testing. It means that if you could achieve 10 to 9 in 15 minutes, it's be possible in 30 minutes. Okay, 10 to 9 is not so big, but if you want to do 10 to 12, the difference will be so bigger. It's about months of difference. So here we have a schema of the pulse and also the pulse of the frequency. So we have do the measurements of the temperature profile of the specimens with a thermographic camera. Here we have the results of the parameters of the thermographic camera. And here we have the temperature against the number of cycles for the materials. Here we have the lowest amplitudes that you use during the testing. This here, every coupons runs out until 10 to 7. Here also, all coupons runs out with a very lower tension, but we can see here also increase in the temperature according to the characteristic of the pulse that you want to do. If, for instance, you use loading 300 milliseconds and pulse from 200 milliseconds, you can see that there is a different change from about room temperature to about 100 centigrades. Very, very different, this situation, just combining pulse and pulse in the specimens. And the situation will be more drastically bad if you are talking about the 40% from the ultimate strength of the material. So these specimens here failed with a temperature between 400 and 550. Here you also have failed specimens between 320 and 530. Also combining the different pulse and pulse. And here we can see the temperature gradient theta in failed specimens. Here we have for this condition of pulse and pulse, for the three conditions of pulse and pulse, by the 40% of the ultimate stress, by the 45% of the ultimate stress. And here, in this graphic, we see this temperature gradient, theta, according to the number of cycles of the specimen. And we can see that increasing the number of cycles of the specimens, this gradient goes down. So we try to modeling these steps according to the heat dissipation of the specimens and in the number of cycles to failure with the first law of thermodynamics. Use the Q, exactly the heat dissipation that comes from the first law of thermodynamics, materials parameter, and also we call it the effective frequency. The effective frequency means that during, for instance, the pulse, the specimen is not loaded. So you have 2 kilohertz, but it doesn't work all the time in the material. So for these conditions of pulse and pulse, we have, for instance, from 20 kilohertz to about 11.6 kilohertz. And with this here, we tried first to doing a machine learning model, a training model, to the data that was predicted, that the model predicted, and the data that was observed during the testing. And also here, the predicted and the observed data by temperature increasing against the number of cycles. It was the first test to see if the algorithm was okay or not okay. And after that, we try to modeling exactly all conditions that we got. Not all, we got only 5 conditions, but there is a plenty of conditions that you didn't use in these simulations, between the lowest effective frequency and the highest effective frequency. So also the tests in agreements, and you see here the dispersion of the temperature against the number of the cycles. What it means? It means that each parameter has a contribution for the final temperature of the specimens. So you see, due to the algorithms, that is possible to see the contribution of the tension of the amplitude during these tests, the number of cycles that intend to achieve, the time of pulse, and also the time of the pulse. You see that the time of the pulse is the lowest, has the lowest influence all over here. The most influence of both then for all this is exactly what go on with the amplitude of the specimens. So, the conclusions, the TN curves of failed specimen temperature increase were observed associated with the reduction of the test time. Specimens tests at intermittent loads, and also by 40 and 45% from the ultimate strengths, presented shortened fatigue life compared to those tested by 110 loading, microseconds loading, and 300 microseconds pulse. Combining high values of effective frequency and amplitude, testing amplitude, results an increase of the theta, the gradient. The most aggressive condition was the highest loading time and the lowest pulse time, with the highest strength of the material subjected to material, increase about 25 times in comparison with the lowest situation from the 50%. The number of cycles to fail increase as the dissipation parameters of the material decrease. The model interpretation reveals the most influence feature in temperature increasing. Based in the machine learning curves, can be said that the model presents a high efficiency and make possible to identify the best combination of parameters in order to minimize overheating specimens during the test. So, thank you very much for your attention.